The matter surrounding us, whether in solid, liquid or gaseous forms, is composed of atoms that are often organized into molecules or, in the case of many solids, into structured lattices or networks. Atoms are composed of a central nucleus and surrounding electrons, similar to the arrangement of the Sun and its orbiting planets. The nucleus consists of neutrons, which have no charge, and protons, which are positively charged particles. Electrons, which carry a negative charge, orbit around the nucleus, creating a balance in electrically neutral atom. There are many different types of atoms, each with a unique number of protons, which defines its chemical identity. All known elements are organized in a periodic table. For example, the simplest atom, hydrogen, consists of one proton and one electron. In contrast, a helium atom has a nucleus made up of two protons and two neutrons, along with two electrons. As another example, the most common unstable carbon is carbon-12, which contains 6 protons and 6 neutrons. If 2 neutrons are added to the nucleus of carbon-12, it is no longer carbon-12 but becomes carbon-14, a radioactive isotope of carbon. Unstable isotopes undergo spontaneous disintegration, meaning that the nucleus breaks apart, forming one or more lighter elements. During this process, it may emit particles such as electrons, alpha particles, or gamma rays. This entire process is known as radioactivity. Like light, gamma rays can travel great distances through the air and can therefore be detected from afar. In contrast, emitted electrons, also known as beta particles, collide with air molecules, causing them to slow down rapidly. If they have low energy or low velocity, they can be stopped in less than 1 millimeter. At higher energy, they are typically stopped within an average distance of a few centimeters. Therefore, they cannot be detected from far away. Most of the time, the disintegration of isotopes emits gamma rays. However, sometimes only electrons are emitted, making detection more difficult. For example, Krypton-85 or Tritium, an isotope of hydrogen, fall into this category and are therefore challenging to detect. Certain human activities, such as electricity production in nuclear power plants and the associated fuel reprocessing, artificially produce these beta-emitting radioactive isotopes, notably Krypton-85, carbon-14, and tritium, and they must be monitored for environmental and operational safety reasons. A scintillator is a material that emits a flash of light whenever a gamma or beta particle interacts with it. It is widely used to detect them. As previously explained, detecting electrons in air is more challenging. To address this, we need a scintillator that allows gas to penetrate it, which we achieve with a porous scintillator. This is the concept behind the scintillating sponge. One challenge is that this sponge needs to be transparent so that flashes of light can pass through it and be detected. To achieve this, we use scintillating nanoparticles, known as nanoscintillators, which are small enough to scatter minimal light. We can assemble these nanoscintillators into transparent sponges known as scintillating aerogels. The gas to be analyzed penetrates the sponge, and if it contains radioactive isotopes, an electron is emitted with each decay. The emitted electron interacts with nearby matter, producing a flash of light. This flash emerges from the aerogel and is detected by photodetectors, generating an electric signal. With the European Photopen SPARTE project, we aim to develop an easy-to-use detector that covers the entire territory, enabling us to monitor the radioactivity produced by human activities in real time and at a limited cost. This would represent significant technological progress compared to the existing methods and address a large global market.